Um, Back by popular demand is Edward Leung from Invesco. So Edward presented at our last online summit and got rave reviews. So delighted to have him back with us. So Edward, you can hear us and we can hear you.
Can you hear me? See me?
Yes, we can.
Great.
Indeed. So great to have you back, Edward. And I thought just one little data point is of the vendors that we have taking part in our alt dating program this year, just over 50% claim to be applying either machine learning or artificial intelligence, or indeed both. So really good to get a practitioner's perspective on these topics. So over to you, Edward.
Great. So should I share my screen?
Please do.
Wait.
This is looking good.
Okay. So you can see the slides, right?
I can see the slides, yeah. So if you just put those in full screen, whatever the PDF equivalent is, I think we are looking
all right.
good.
Okay, so thanks for having me. I'm a senior quantitative analyst at Invesco Quantitative Strategies, and today I'm going to talk about this question: what is the promise or pitfall of machine learning in alternative data? So, I think in order to answer this question, there are several things that we need to understand before we actually get the answer. So we need to understand, what systematic analysts actually do with traditional data, and what kind of issues do they come across with traditional data, and also how can machine learning help them to alleviate some of these issues, and then we can add the picture of alternative data on top to see, how things how this issue change with the emergence of alternative data. So and then I'm going to talk about some examples on text data, and the purpose of this talk is really to provide an overview of some of the academic research out there that sort of that shed light on these questions and come up with possible answers to the big questions of the relationship between machine learning and alternative data, and the promises and pitfalls. So, a lot of us, that are systematic, do factor investing. So basically, factor investing is an approach to capture systematic returns premier via transparent and rule-based portfolio construction. So the goal is basically to capture various sources of returns, such as size, value, momentum, and profitability, while looking at the benefits of diversification and reduce unintended exposures. So in recent years, there's this whole emergence of a factor zoo. So this chart that I have in the bottom is very telling. So as you can see, from the 1920s, when we only have Moody's data, all the way to 2019, when we include the SEC Edgar database, there's a sort of a linear positive relationship between the megabytes. So you can see the y-axis as the storage or the amount of data out there, and the x-axis, which is the number of variables, so or factors. So as there are more and more data, emerging, there are also more and more factors to look at in terms of evaluating their efficacy in terms of predicting returns. And one thing that we do often is to run these sort of cross-sectional regression in each time period. So as you can see from this equation, the left-hand side variable, the dependent variable is stock returns, and then the right-hand side are basically exposures of each different factors. And say, when for each date, you're looking at the Russell 1000 universe or Russell 3000 universe, the number of observations for each date is probably 1000 or 3000. So as there are more and more factors emerging, you can see that there's a possibility that the number of factors is actually more than the number of variables that you have. And in this case, this type of multivariate regression will not have a unique solution. or even when the number of factors are close to the total number of observations, the regression will overfit noise because it doesn't have enough degrees of freedom. So, some research that my colleagues, Harold Loker and his friends wrote about is to provide some guidelines in terms of helping us to navigate through this factor zoo by focusing on evidence, sort of relevant to practicalities of factor-based investing strategies. So, as you know, people, some of the panelists earlier already mentioned, having a strong rationale, investment rationale is a key to identify a true factor, and we have to be aware of data mining. So a lot of these factors that are common out there, like book to price, momentum, they all have very strong rationale, and also we have to be aware of multiple testing. So when we have more and more factors, we not only sort of magnify the issue of this factor zoo, but we also have this problem of data snooping and multiple testing. So we need to adjust the statistical significance for multiple testing. So a good example is basically this whole idea of multiple testing is that when you look at the same set of data many times, then you're bound to find something significant by chance. So for example, if you, and to be more precise, the definition of multiple testing is really just sort of performing more than one statistical inference procedure on the same data. And for example, when if you see a manager out there that outperformed the market for 10 years in a row, you would expect the performance to have a very, very high statistical significance. So meaning an extremely small p-value, like less than 0.001 or something. But what this p-value fails to account for is that there are other managers out there. So if there are 10,000 managers that are unskilled by random chance, you expect 9 of them to also have 10 consecutive years of outperformance. So as a result, you cannot just look at the p-value of that particular manager alone. You have to sort of adjust the statistical significance to deal with this multiple testing issue. And also, a lot of the academic studies out there, they also include a small cap, very small micro cap stocks. So it's important to sort of filter them out to see if you still find a lot of these factors to be relevant. And the last point is to check for the efficacy of the factor. We need to look at a multiple asset class. So we have to test it not only in equities, but we have to test it in fixed incomes or even commodities. So so now that we know that the issue with us is that there are lots of factors. The fact that the number of factors are exploding. We don't know which one that are relevant in terms of true performance. So how does machine learning actually contribute to factor research that can with traditional data? One thing is machine learning usually improve the out of sample R square. So because a lot of these machine learning tools are actually variable selection and dimension reduction tools. So they help us to sort of navigate through this factor zoo and sort of get and only look at the factors that are relevant. The other point is that machine learning looks at non-linear model. So they can sort of evaluate whether there are any value added of looking at using a non-linear model to predict stock returns over a linear model. But investors only care about portfolio outcomes. So does having very high out of sample R square translate into economic gains in real-time portfolio management? So one research that me and my colleagues have published in the Journal of Financial Data Science this year is sort of examining that. Outside research has a lot of the research out there has showed that the machine learning models dominate traditional linear models in predicting cross-sectional stock returns. So what we did is that we try to confirm these findings by predicting 1 month forward-looking returns based on a set of common stock return characteristics like momentum, quality, value, and short-term reversal. And after we confirm that, we take this machine alpha that is being built by machine learning and use this as an input in 3 simulation settings with more realistic real-world constraints such as sector, industry, transaction costs, and all that. And at the end, we find that once we take that into account, the value added of having a machine that of machine learning models over linear models has diminished. So in short, it's not always the case that high out of sample R square can translate into economic gains in portfolio management. So now that we talk about sort of issues that we face with the emergence of lots of factors of the factor zoo and also the multiple testing and all that. So now we can add sort of the alternative data back into the picture. This table sort of listed sort of typical asset pricing applications with typical machine learning applications. So the first difference is signal to noise ratio. In other fields of study, they typically have very high signal to noise ratio, whereas in asset pricing we have very low signal to noise ratio, and that's because returns are very noisy. And in other study, when you're trying to train a machine to recognize a hot dog, that's not a very noisy problem. Data dimension. Other fields in science, they have many predictors, but they also have a huge number of observations in the range of millions. But in finance, in asset pricing, we have a factor zoo. We have a lot of predictors, but relatively few observations. So as we mentioned, and we want to run a cross-sectional regression for each month or each date, we might only have at most 3,000 to 5,000 observations. Aggregate level of interest. So again, as I mentioned, in typical machine learning application, they only care about the accuracy of the prediction, whereas in our case, we care about portfolio outcomes. So that means that even if I'm able to build a model that has very good prediction of stock returns, but when I take that and rank these machine learning alphas into a hedge portfolio and look at the return spread or return ICs, they may not be as strong as the R square of the individual regression. The last point is stationarity, obviously, and a lot of the outside research that are not in finance, the data is stationary, whereas in finance or asset pricing, ours is not, because investors tend to learn from the data and adopt to the behavior. So and also in this, so within all these points, an obvious impact of the emergence of alternative data is alternative data adds to the factor zoo. So it make it so the traditional factor zoo is already huge. So now we have even a bigger factor zoo. So one example, another aspect of how alternative data can magnify the factor zoo is that alternative data, kinds such as transaction data or GPS data or text data, tends to be available in higher frequency. So like in monthly, weekly, or even daily. But but then variables that we're interested in, like returns or fundamental data, like earnings surprise or they tend to be only available in monthly or even quarterly. So how do we use this higher frequency alternative data to predict lower frequency variables? So in a sense, we want to align our data in such a way that we can update these forecasts of the lower frequency variables as as the higher frequency data comes along. So this alignment causes additional lag predictors into the regression model. So here we have a, on the left-hand side of the page, we have sort of like a data set. So we have, say, we have sort of a quarterly, we're trying to predict quarterly data, which is Y, and then we have predictors such as monthly data, X1, or weekly data, X2. But when we sort of align this data and put it into a regression framework, you can see that, now we have, 5 additional variables. So monthly data from X1 to X6. So we have an extra, our data frame becomes bigger. So that makes the problem of having too few degrees of freedom even more severe. And if we add these, weekly variables in there, then we can see that in additional to the data frame that has monthly data, we have additional lag variables that have that has weekly data. So, for example, on line 1, we're using sort of weekly data from week 1 to week 24 and month 1 to month 6 to predict sort of quarterly data at period 2. So in short, these alternative data significantly increase the number of predictors by itself, and also increase it through lag predictors during this realignment. So in a sense, we need tools to help us to limit the number of factors to a reasonable amount, and so that we have sufficient degrees of freedom. And also we need to have a tools that can help us to navigate through these lag predictors that are highly correlated with each other. So, these are some of the possible solutions offered by academic research. So again, for the first and foremost is economic intuition, like some of the panelists says. For example, when we test consumer transaction data, we know that real-time sales information should be able to predict earnings. So we should sort of verify that conjecture first, and if it works, then we can look at sort of whether consumer transaction data can predict returns. And also some of these research out there, like like Lego and Martin built a Bayesian model where investors learn from the observed data to see what variables are good for predicting returns. Also, there's some research by Fang and Giglio that apply Lasso as a variable selection tool to select the relevant variables. And then some research by Nago and Barbie that show that Lasso actually does not perform well when predictors are highly correlated. So they use something, and Nago actually shows that an elastic word net actually works better, and Barbie balls and Friso, they actually show that sparse group Lasso actually works better. And then there are some, Gu and Kelly, they actually use a autoencoder neural network as a dimension reduction tool. So basically that is like a nonlinear or a neural network version of a principal component. And then, another way to do this is to just build lower complexity models. So again, this Kelly paper finds that shallow learning actually works better with small data instead of deep learning. And another way to sort of make the data less noisy is to smooth them out. So there's some research out there that show that instead of trying to predict 1 month return in a machine learning model, you can try to use a predict cumulative 6 months or 12 months return. That will actually certainly smooth out the data and to make the data more stable and less noisy.
Edward, while you're on a slide with lots of references on it, one question from the audience is a quickfire one, which is top 3 journals that you read. Is the question, is what are the top 3 journals that you recommend?
Well, I think now that machine learning and in finance is so common, I think the Journal of Financial Data Science, which is a new journal, is certainly worth reading. And then obviously for us, which are practitioners, we journal portfolio management, journal financial data science, and probably those two, or maybe more academic journals like Journal of Finance or Review of Financial Studies.
Awesome, thank you. And Edward, sorry to hurry you. I think we have you slotted for another 2 or 3 minutes.
Oh no!
So I know you have a few more slides to go, but I'll give you an extra minute, Edward. But yeah, just wanted to give you a bit of advance warning.
I see. Then, yeah, let me just then, in that case, I'll just skip some slides then. Basically, you know, this slides are saying that, you know, how does alternative data machine learning fit into our investment process? So, you know, most of the alternative data are also big. So maybe, you know, instead of trying to apply machine learning to factors and trying to build and trying to come up with alpha to predict returns, maybe it's more beneficial to apply machine learning to this unstructured alternative data source, and then convert it into a structured data source as a factor, and then use that to build an alpha to predict returns. And we did some, and I think, and one of the good example of this is actually text data. So there are lots of research out there that applies NLP to unstructured text data and convert them into sentiment factors, and then use these factors to predict returns. We have done, at IQS, we have done a lot of work using NLP and text data. We have applied NLP to form a sentiment factors on earnings transcripts, and then we also use NLP to find companies that exposed to mega trends that will shape the future. So it's kind of like a thematic approach. And what is the current biggest agenda? I think the thing that is on the research agenda, it will be ML ops. So it's kind of like a machine learning pipeline. So basically, you're trying to build a fully automated machine learning pipeline from data ingestion to model building all the way to deployment. And then some of the machine learning research out there that are probably promising in finance data, because as I said before, finance data are small relative to other big data. So there are transfer learning and few shot learning. That these are sort of machine learning approach that will alleviate the issue of small samples. And at the end, you know, I hate to give you the sort of like the banal answer, but what is the promise and pitfall of machine learning in alternative data? The answer is it depends. It depends on how you use it. We need to be mindful of how we apply machine learning applications, and blindly applying off-the-shelf machine learning tools and asset pricing is not going to give satisfactory results. So we have to. So in general, you know, alternative data and enlarge the factor zoo and magnifies multiple testing. We need a sound theory to pick the variables. It's probably fruitful to apply machine learning to convert raw data into structured data and then use it to build factors. And related to your question, Ian, is that we need to pay attention to data science research, given not just quantitative finance research.
Well, the other questions coming up, Edward, are mostly around whether you'll be able to share the slides. So we'll take that as a good sign that this was a hit with the audience again. So thank you so much. I guess there's a really interesting question there that comes up around how can the vendors also use machine learning, in the sense that you're advocating that someone, whether it's your side or the vendor side, should be using machine learning to build the structured data. So I think that's a really sort of great segue onto three vendors who are really active in that space. So thanks so much, Edward. Really enjoyed that. And
thank you.
Great connection to what we have coming up next.